In this video, we're going to discuss generalized continued fractions. So what does it mean to generalize continued fractions? So here's one approach one can take. Suppose you have arbitrary real numbers, ai and bi. Now here on the left, we have something that looks pretty similar to our continued fraction notation. We start with a naught, but then in each index, rather than just putting an ai, we have a bi and an ai. This doesn't really represent a fraction. What it represents is the pair bi and ai, because the b's now take the place of these numerators. A's are still doing what they did before. In other words, we're building a nested fraction where the numerators are not necessarily 1. The numerators are kept track of by the sequence of b's. However, if this terminates at some point, you could still compute this to be sum pn over qn. In fact, they don't have to be real numbers. They could, for example, be integers, in which case the Pn over Qn will still be a rational number, and that's typically what's going to happen. One can prove by generalizing, for example, Gaussian brackets. We're not going to go through those details, but it's not that hard once you've seen it done in the regular continued fraction context, that we have a very similar recursive formula for generating our p's and q's. Still, p naught is a naught and q naught is 1. If the continued fraction expansion terminated here, you would just have a naught over 1. Great. If it terminated here, it's not that much work to see. You'll get a naught a1 plus b1 over a1. So there's p1 and q1. And then the recursive formula looks pretty similar to what we had before, except instead of just having the next p and the next q be the next partial quotient times the previous p and q plus the previous p and q, this term here gets multiplied by the b's. Okay, now the index on b is still the index that you're constructing, so there's a difference of 2 in the index there. The an's, by the way, are sometimes called the partial denominators rather than the partial quotients, and the b's are called the partial numerators. Now suppose you have a given sequence of an, bn, and then pn and qn. If the pn and qn converge to some value of x, then we can say that this infinite generalized continued fraction represents the number x. Now, because the b's might, for example, be negative, you may end up constructing a q that's 0. And then one of the pn's over qn's might have a denominator 0. That would be a problem. That's actually generally considered okay, as long as it only happens finitely many times, in which case, if you go past that index, it will never happen again. So this is a minor little caveat, and once you have negative numbers thrown in here, things can get a little strange, but as long as only finitely many of the denominators work out to be 0, it's generally considered fine. Back in the land of regular continued fractions, when we computed these pn's and qn's, we were able to prove that the pn over qn as a rational number and a sequence of them always converged to something. Now for generalized continued fractions, unfortunately, that may not hold. So here's an example. We have the generalized continued fraction that starts with a 0, then 1 over 1, then negative 1 over 2, negative 1 over 2, and it stays negative 1 over 2 from that point forward. Show that that generates pn's and qn's so that pn over qn does not converge to anything. So note that once we hit index 2, the partial numerators bi are always minus 1, and the partial denominators ai are always 2. The first two terms, a0 and b1 over a1, are slightly different, but after that we always have negative 1 over 2. So if we compute the first terms for index 0 and 1 using these anomalous partial numerators and denominators, we get 0 over 1 and 1 over 1. Now let's assume that for some index at least as large as 1, pn over qn is n over 1, and pn minus 1 over qn minus 1 is n minus 1 over 1. Then, once we've moved past index 2, so an plus 1 and bn plus 1 are at least index 2, so a's are always 2, and the b's are always minus 1. We've inductively assumed this is n over 1, and n minus 1 over 1. And this works out to be n plus 1 over 1. So assuming we have two consecutive terms that are just index over 1, then the next term also does that. And look what we proved. P0 over Q0 is 0 over 1. P1 over Q1 is 1 over 1. Therefore, Pn over Qn is always n over 1. That does not converge to a real number. So we have an infinite generalized continued fraction that is not converging to anything. Now here's a theorem of Euler. For arbitrary numbers b0 through bn, on the left we have this sum of growing products. So we have the sum going from index 0 to n. This index I is keeping track of where the product ends. So this will start just going from 0 to 0, b naught. Then it will go from 0 to 1 of b naught times b1, and we keep adding those up until we go all the way to this term here. So Euler has proved that this sum of products is equal to this nested fraction. Okay, which can now be represented as, note that there is no number being added here, so we start with a 0, then b naught over 1. After this point, we have a pretty regular pattern. Minus b1 over 1 plus b1, minus b2 over 1 plus b2, and so forth and so forth. So after the 0 and the b naught over 1, we have a minus bi over 1 plus bi, and that continues until you get down to the end here. So we're going to prove this by induction, which isn't too surprising. Note that the expression does change a little bit when n is 0 versus other terms. This fraction has different things going on once you get past the b naught over something. Past that term, the pattern looks a little different, so we're going to have to prove it a little differently for index 0 and 1. So we're going to do two base cases. Now for n equals 0, on the left we just have b naught. And on the right we would have b naught over 1. Hooray, that is true. For n equals 1, we're going to have b naught plus b naught b1. And on the right, we'll have b naught over 1 minus b1 over 1 plus b1 right here. Now, all you have to do is do some arithmetic, multiply both numerator and denominator by 1 plus b1, and observe that down in the denominator, these b1s cancel, and here we get b naught plus b naught b1. That's exactly what we want, over 1. Okay, so now let's assume that the identity holds, the one at the top of the page, for some index n bigger than or equal to 1. The only reason we had to prove two base cases, by the way, is because the formula does look a little different at index 0. So our inductive hypothesis is that whenever we have a collection of numbers matching this pattern, starting at index whatever, okay, the particular numbers don't matter as long as we count up from some index, end at a term that has n larger, meaning this product, by the way, has n plus 1 terms in it. So we have n plus 1 terms in the sum here, will be represented as this generalized continued fraction. We've assumed that this holds for any collection of numbers ending at some index n larger than or equal to 1. Now let's look at what happens when we end at index n plus 1. This term b naught, let it hang out by itself. From everything else, factor out a b naught. And now what do we have inside parentheses here? Exactly something that looks like this by shifting all of the indices up by 1. Okay, remember, the exact numbers here don't matter as long as it's this pattern, and that's what we're going to end up with here. Once you factor a b naught out of all of these terms, you'll have exactly b1 plus b1 times b2, b1 times b2 times b3, all the way up to this, which is exactly what we made an inductive hypothesis about, can be represented as this continued fraction, just with all the indices increased by 1. So do so. We end up with a nothing, a b1 over 1 minus b2 over 1 plus b2, etc. So that's exactly what we have here. Now to make our lives writing this out a lot easier, I'm just going to call this b naught plus b naught times b1 over 1 minus c. This whole expression where the pattern is holding b2 over 1 plus b2 minus b3 over 1 plus b3, etc., that's what I'm denoting as xi. Just so that writing this is simpler going forward, and the exact thing of xi will come back at the end, but for now it doesn't particularly matter. So factor b naught out of both terms. Now I have a 1 plus b1 over 1 minus xi, so I'm going to call that 1 minus xi over 1 minus xi, just to give these a common denominator. Now to get from here to here, divide numerator and denominator by this parenthetical term, canceling it out of the numerator, introducing it down into the denominator. And then here, 1 minus xi, we're going to do the classic trick of adding and subtracting the same number. Okay, so this is just a bit of algebraic trickery. But now look what we have down in our denominator. We have this over itself minus b1 over that. So 1 minus b1 over that. But now look what happens. If you were to replace xi, that was b2 over 1 plus b2, etc. So we have b naught over 1 minus b1 over 1 plus b1 minus b2 over 1 plus b2 all the way down to index n plus 1. That's exactly the general pattern we were hoping to establish. We've completed our inductive proof. So what we've established is that for any sum of products of this pattern, it can be represented through a very specific generalized continued fraction. If you take a limit as n goes to infinity, assuming one side converges, the other one must as well. Okay, so on the left we have a certain series, an infinite collection of sums. And on the right, we'll have a continued fraction, a generalized continued fraction. So if we can establish that the series on the left converges, well then, the generalized continued fraction on the right must converge to the same thing. So for particular interest, suppose that b naught is 1, but otherwise bi is x over I. So we're going to have a 1 times x over 1 times x over 1 times x over 2, and so forth. On the left, we get this, 1 plus x over 1 times x over 2, x over 1 times x over 2 times x over 3, and so forth. And this series is the power series for e to the x. It converges to e to the x regardless of x, meaning the right side must also converge to e to the x. So what we've actually established is that the power series on the left is e to the x, but on the right we would end up with this generalized continued fraction, 1 over 1, negative x over 1 plus x, negative x over 2, 1 plus x over 2, all the way to negative x over n, 1 plus x over n, but it just keeps going. We have the limit as n goes to infinity. Okay, so we can represent it as this kind of huge, ugly, nested continued fraction. Notice that our numerators have their own numerators and denominators and so forth. But this does converge, meaning algebraic and arithmetic manipulation is pretty freely allowed. So what we're going to do is I don't want this to be x over 2. I'd rather it was just x. So multiply by 2 over 2. If I multiply this parenthetical term by 2 over 2, its numerator just becomes x. Down here I get a 2. This becomes an x, and now this whole thing gets multiplied by 2. So I've called this 2x over 3. Okay, so we've got e to the x is this huge nested continued fraction, but now I don't want this to be a fraction, so I'm going to multiply this parenthetical term by 3 over 3. I haven't changed anything here. I'm just multiplying this by 3 over 3, meaning this just becomes 2x. Now I get a 3 plus x, and so forth and so forth. This ellipsis down here is going to get multiplied by 4 over 4, etc., etc., etc. And if you keep doing this ad infinitum, you get the following. Okay, we get a 1, an x, and an x. Then we're going to get a 2x, a 3x, a 4x, and so forth. So these partial numerators are just successive multiples of x. Starts a little different with a 0 and a 1 and a negative x. Then minus 1x, minus 2x, minus 3x, and so forth and so forth. And our denominators start a little different as well. This doesn't have its own denominator, then 1. But now it's 1 plus x, 2 plus x, 3 plus x, and so forth and so forth. So observe that this number is just 1 less than that one. And it particularly works out to be n minus 2 here and an n minus 1 there. Now, if we particularly set x equal to 1, we will exactly on the left have e to the first, e, and on the right we will have a generalized continued fraction representation of the number e. Specifically, this. It's a pretty nice little pattern. So it starts with 0 and 1 over 1, but then it's minus 1 over 2, minus 1 over 3, minus 2 over 4, minus 3 over 5, minus 4 over 6, and so forth and so forth. So what we've done is we've found a generalized continued fraction that represents the number e, which is mildly, at least, interesting. The a's, the partial denominators, follow a very nice pattern, 0, 1, 2, 3, 4, and so forth. The b's start off with a couple exceptions, starting with a 1 and a minus 1. After that, they have a very nice pattern of minus 1, minus 2, minus 3, and so forth. So let's compute some p's over q's and see how they relate to the number e. The first thing we're going to get is 0 over 1. That's a pretty bad estimate for e. 1 over 1 is better, 2 over 1 is even better, and the next few terms we get after this are 5 over 2, 16 over 6, 65 over 24, and so forth. I've given you a couple more. Now think back to what about this is looking different than regular continued fractions. So in regular continued fractions, your sequence of Pn over Qn alternated between bigger than x, less than x, bigger than x, less than x, and so forth and so forth. All of these are less than e. They're converging to e, but they're all less than it. So we lose that alternating property. Also, the Pn's and Qn's are not necessarily relatively prime to one another. Some of these fractions could have been reduced, specifically 16 over 6, 326 over 120, and there will be infinitely many more. In fact, it's straightforward to compute. that Pn plus 1 Qn minus Pn Qn plus 1, back in the land of regular continued fractions, this was always a power of minus 1. So in absolute value it was 1, and this was our proof that the Pn and Qn are always relatively prime to one another. But here, if you make your recursive substitution for Pn plus 1 and Qn plus 1, there's going to be a Bn plus 1 that factors out in absolute value. If all of the b's were in absolute value 1, then just as in regular continued fractions, you'd get a nice inductive proof that the pn's are always relatively prime to the qn's. But when the bi's can be larger integers, you lose this result. And if you in fact work with weirder generalized continued fractions where you're allowed arbitrary real numbers, then this doesn't even make a lot of sense anyway. However, if we make the restriction that the ai's have to be integers and the bi's have to be plus or minus 1, you get sort of the weakest generalization you can of regular continued fractions. Okay, the a's, except possibly the first one, are all going to be positive integers, in fact, and the b's, not just 1, but maybe also minus 1. You're still going to be able to derive that the fractions Pn over Qn are always reduced. Pn is always relatively prime to Qn. That situation is called semi-regular continued fractions. It's almost regular continued fractions, and we'll talk more about that in a bit. For now, let's keep revisiting this formula of Gauss. So for a function f of x with infinitely many derivatives at x equals a, and none of those derivatives are 0, let's say, let's just go ahead and set b0 to be f of a, b1 to be f prime of a over f of a, which we assumed wasn't 0, times x minus a over 1. This is f double prime of a over f prime of a, which we assumed wasn't 0, over times x minus a over 2. And in general, the nth derivative over the n minus first derivative, and we assumed none of those are 0, times x minus a over n. Well then, what do these products start to compute? Exactly a power series for f of x centered at x equals a. It's the Taylor series. So using general calculus techniques, you may already know that the Taylor series for the function f of x is converging to the function f of x. Let's just presume that that works out at x equals a. In which case, the continued fraction on the right will also be converging to f of x. So then a known value of f of x might produce interesting generalized continued fractions. In fact, any way you can get the series on the left to generate the known power series of a function will work. This general form here works as long as none of these are being divided by 0, but really any way you could finagle this to start looking like a power series or Taylor series for a function that you already know converges will give you interesting continued fractions on the right. As a particular example then, let's consider the function arctan of x. Arctan of x has a well-known power series expansion centered at 0. It's an alternating sum of odd powers of x divided by whatever that odd power was. How are we going to make that look like the series we need to apply Euler's continued fraction formula? Well, this has to be exactly b0. This now has to be b0 times b1. So this is x times what? We need to introduce a minus, 2 more powers of x, and a 3 in the denominator, so minus x squared over 3. Then what would I multiply this by to get to our next term? 2 more powers of x, flop from minus back to plus, cancel this 3 and turn it into a 5. So cancel the 3, turn it into a 5, add 2 powers of x, and a minus. And in general, this is how you're going to get from one term to the next. This general minus here says you're just going to keep alternating back and forth as you multiply them together. You cancel the previous odd number and introduce the next one into the denominator and add 2 more powers of x every time. So the product of b0 through bn, if you multiply all these together, well, how many minus 1s do we have? For index 1, 2, up to n, so we get negative 1 to the n, but observe not a minus sign here, so only negative 1 to the n. How many x's? 2 of them for index 1 through n, that's 2n, plus 1 more, so x to the 2n plus 1. And what number do we have in the denominator? A 1, then a 3, cancel the 3, make it a 5, cancel the 5, make it a 7, cancel the 7, make it a 9, all the way until we introduce 2n plus 1. So this product here of b0 through bn will exactly be the general term of the power series for arctan. So on the left of Euler's continued fraction formula, I hesitate to call it Euler's continued fraction formula. Euler has a lot of formulas named after him, but the one we've been using. On the left, you're just going to get arctan of x. Therefore, on the right, this continued fraction expansion, this generalized continued fraction, must also be converging to arctan of x. So now we just have to compute that. Okay, well, negative b1 is going to exactly cancel this minus sign. Negative b2 will exactly cancel this minus sign, and so forth. Setting x equal to 1 is then going to give me once you cancel out this minus sign, because that's our general formula, we're going to have 1 over 1 plus 1 over 3 over, and when you do 1 plus this, you're going to get 2 over 3. And that's going to kind of continue. You're going to get this 1 over 1. These numerators, we've canceled out all of these minuses because in Euler's continued fraction formula, they all do have a minus attached to them. 1 plus that means I just take this right here and I'll have 1 minus a third, 1 minus 3/5, 1 minus 5/7. What always is missing is 2 out of whatever that odd number is. So this gives an expression for pi over 4 being arctan of 1. And it's this generalized continued fraction where all of our partial numerators and partial denominators are themselves fractions once you get past this 1 over 1. But we know this converges to pi over 4, so we can do a lot of arithmetic on it pretty freely. For example, let's multiply this whole expression by 3 over 3. That's going to turn this numerator into a 1. Turn this into a 2, but now here I'm going to get a 3 squared over 5. Well, now this parenthetical term, I'm just going to multiply by 5 over 5. If I multiply this by 5 over 5, it cancels this 5 out, leaving behind 3 squared. It cancels this 5 out, leaving behind 2, but now this becomes a 5 squared over 7. If I keep doing that, I'm going to multiply this by 7 over 7, then what comes next by 9 over 9, and so forth. I'm always getting a 2 here. When I multiply this by 7 over 7, I'm just going to get a 2. 2, 2, 2, 2, 2, 2, 2, 2. What's happening in our numerators? 1 squared, 3 squared, 5 squared, 7 squared, and so forth and so forth. So we end up with this kind of nice looking generalized continued fraction expansion for pi over 4. Once you get past this 1 over 1, it's 1 squared over 2. 3 squared 2, 5 squared 2, 7 squared 2, 9 squared 2, and so forth and so forth and so forth. Sometimes this is reciprocated to make the pattern look a little nicer. You may also subtract a 1 so that the pattern starts right away and so forth. But whatever, you have a nice generalized continued fraction expansion for pi over 4. There are lots of ways to use Euler's continued fraction formula combined with power series to get nice generalized continued fractions for lots of constants. E, the natural log of 2, pretty much anything you can come up with. As long as it is expressed as a known value of a function for which you know the Taylor series converges at a specific point, you can exploit this little trick to get nice generalized continued fraction expansions for constants. So now let's talk about those semi-regular continued fractions. Basically, you have all the restrictions of regular continued fractions where your AIs are integers, and in fact, for index 1 or larger, they're positive integers, but you throw in that the numerators bn are plus or possibly minus 1. So that's the only change from regular continued fractions is that your numerators might be a minus 1. These are called semi-regular continued fractions. We're going to be able to recover some results from the theory of regular continued fractions because this is pretty similar. So let Pn over Qn be the convergence to the semi-regular continued fraction. Then for all n, the absolute value of Pn, Qn plus 1 minus Pn plus 1 Qn is 1. In regular continued fractions, this quantity specifically alternated between plus or minus 1. We're not claiming that anymore. What we are is claiming that it's always an absolute value 1, but maybe not strictly alternating plus minus 1. Well, for n equals 0, we end up with the absolute value of P0 Q1 minus P1 Q0, which just computes down to the absolute value of B1, which is 1. I mean, strictly speaking, it's the absolute value of negative B1 if you do the algebra, but that doesn't matter under the absolute value sign. Then assuming the equality holds for index n minus 1, let's look at the next index. Use the recursive formula for Qn plus 1 and also for Pn plus 1. Observe that the quantity Pn, Qn, An plus 1 will cancel, leaving behind just two terms from which Bn plus 1 can be factored out. So it can be factored out in absolute value, and what remains is exactly what we've made an inductive assumption about, that Pn, Qn minus 1 minus Pn minus 1 Qn in absolute value is 1. So this all simplifies down to just what's the absolute value of the next b, and they're all plus or minus 1, so an absolute value definitely 1. So this is very similar to how it works in regular continued fractions. This, by the way, is how you derive that the Pn over Qn are simplified rationals, that the Pn's always relatively prime to the Qn's. So you do recover that for semi-regular continued fractions as well. So semi-regular continued fractions have a lot of nice properties that regular continued fractions have, but not all of them. They're not quite as nice to work with. For example, you can have a semi-regular continued fraction that doesn't converge at all. Show that the semi-regular continued fraction 0, 1 over 1, and then minus 1 over 2, minus 1 over 2, and so forth, generates a sequence of Pn over Qn that don't converge at all. We actually already did this. We showed that Pn over Qn is exactly equal to n, and as n goes to infinity, that's not converging. Also, a rational number, well, a regular continued fraction for a rational definitely terminates, but for semi-regular continued fractions, it might not. As an example, we have the semi-regular continued fraction 2, minus 1 over 2, minus 1 over 2, minus 1 over 2, and so forth. All of the AIs are 2, all of the BIs are negative 1. So P0 over Q0 is 2 over 1. P1 over Q1 is 3 over 2. In general, let's just assume that that pattern continues for at least 2 consecutive terms. I mean, we showed it for index 0 and 1. That Pn over Qn is n plus 2 over n plus 1, and the previous term, Pn minus 1 over Qn minus 1, is n plus 1 over n. Then let's look at the next one. Remember, all of our A's are 2, all of our B's are minus 1. So this works out to be n plus 3 over n plus 2. The pattern continues. So every Pn over Qn is definitely given by n plus 2 over n plus 1, and as n goes to infinity, that converges to the nice rational number 1. We have an infinite semi-regular continued fraction converging to a rational number 1. What we'll see now is that any given number can have many representations as semi-regular continued fractions. In fact, any irrational number has uncountably infinitely many different representations as semi-regular continued fractions, which is way different from the land of regular continued fractions, where, yeah, rational numbers had 2 representations, but they were very similar, and irrational numbers always had exactly 1. Here, irrational numbers always have uncountably infinitely many different representations as semi-regular continued fractions, which is just way different, very much not a one-to-one correspondence. So suppose x has a semi-regular continued fraction expansion, which any irrational x has because it has a regular continued fraction expansion where all of the b's are plus 1. Now here's a bit of algebra to verify. Whatever a, b, and c are, this is plus or minus 1. It's the same thing here. Here it's the opposite. Just verify by giving a common denominator, etc., that the two sides are always equal. Now, what we're going to do is suppose this capital B is like our an. The thing over it is like bn. If this is a minus 1, then this is going to be a minus 1 here, so then I need to subtract 1 from the previous partial quotient, but I want it to still be legitimate. So if I want to subtract 1 and still remain legitimate, if this was a minus 1, then this should be at least as large as 2, so that I can subtract 1 from it. And I know I'm going to subtract 1 from an, which is why we made the assumption that it was at least as large as 2. So on the left, we have our semi-regular continued fraction, a bunch of stuff happening that isn't written. Here's an minus 1 plus bn over an plus a bunch of stuff. What ends up happening is this bn gets added to the previous partial quotient there. Now I have its opposite, so this is minus bn over 1, definitely a plus 1, and I subtract 1 from this an, and now this is whatever happened after that point. So this semi-regular continued fraction, under the assumption an is at least as large as 2, because I need to subtract 1 from it, and if this is a minus 1, this was at least as large as 2, so that this is still valid. These two semi-regular continued fractions are equal to one another. Now we can try to go the other way. Keeping track of pluses and minuses is a little tricky, but if an is 1, okay, this is going to be made 1 larger. There's really no restriction there. But if this is a plus 1, then this is a minus 1, and this is going to get bigger, which is not a problem. But if this is a minus 1, this is a plus 1, in which case this is going to get smaller. So if this numerator is a minus 1, we do require a plus 1 to be at least as large as 2, so that I will have at least 1 here. So then this is our semi-regular continued fraction over here. We've got a bunch of stuff going to an minus 1 plus bn over 1 plus 1, because we did assume bn plus 1 is 1, and then a bunch of stuff that happens after this point. Here's an plus 1, and here's all the remaining terms after that. To go this way, this 1 essentially vanishes. Okay, we end up with a plus bn here. Again, this is what I think is the trickiest thing to keep track of. If bn is negative, then this is a plus 1, but then I'm going to subtract 1 to end up here. If bn was positive, then this is a minus 1, and I'm going to add 1 to get over here. Either way, we just had a plus bn. This got exactly reversed. Here's my minus bn. This an plus 1 gets increased by 1, and then after that point, nothing changes. Okay, and we're actually generally going to be working with this pair of identities under the assumption that bn is 1 anyway, which means this little bit about an minus 1 never comes into play. And if bn is 1, you can actually start to narrow down that this is definitely a plus 1, this is definitely a plus 1. So under that assumption that bn is 1, if an is at least as large as 2, we have the semi-regular continued fraction with a plus 1 over something at least as large as 2. This is equal to add 1 to the previous denominator, put in a minus 1 over 1, then instead of a 1 over an, you have a 1 over an minus 1, and after that point, nothing changes. Whereas the process, if you had a 1 with a 1 over it, here's your 1 over 1. What you do is you add 1 to the previous denominator, add 1 to the next denominator and reverse the sign of its numerator, and then after that, nothing changes. Specifically, we can do this to the regular continued fraction expansion of something to create a semi-regular continued fraction, because now our numerators may have been transformed into some minuses. If you do this in an index where an is bigger than or equal to 2, this is called insertion, because we inserted this term here and modified these two quotients. Okay. If you do it where you have a partial quotient of 1, it's known as singularization, and the origin of that word is slightly technical. But it just looks pretty similar. You're adjusting the values of some nearby partial quotients and numerators, but everything before and after a certain point isn't being changed at all. So now we're able to show that any irrational number contains uncountably many different representations as a semi-regular continued fraction, because the effect is that if you start with the regular continued fraction expansion, anywhere you see a partial quotient 2 or larger, you can perform an insertion and end up with a semi-regular continued fraction. In fact, you can do it over and over again. If you had a partial quotient of 5, for example, if you do an insertion, it gets subtracted by 1 and is 4. But now you can do an insertion again and again and again. So you can keep doing that until you run out of room, basically. When an is equal to 1, as long as the next numerator is plus 1, you can perform a singularization, acting as kind of an inverse to this. So for example, suppose you have a nice regular continued fraction 5 plus 1 over 4 plus 1 over 7, etc. If you perform insertion on the first index, the one before it goes up by 1, then you insert a minus 1 over 1, then the 1 over 4 becomes 1 over 3, and everything after that point doesn't change. But now you can do insertion on that 1 over 3. The denominator before it goes up by 1, you insert a minus 1 over 1, the 1 over 3 becomes 1 over 2, and everything after it doesn't change. You can insert again. Now we can complete the proof that an irrational number has uncountably many different representations as semi-regular continued fractions. Wherever you have a partial quotient 2 or larger, you can choose to perform insertion or not, and you can make a choice about how many ways to do it. Okay, if there are not infinitely many partial quotients bigger than or equal to 2, then past a certain point they're all equal to 1, and you can make infinitely many different choices as to where to perform singularization. Either way, you have infinitely many indices in the regular continued fraction where you can choose how to make an equivalent semi-regular continued fraction. And you can perform insertion singularization on the semi-regular continued fractions you create. In other words, from your starting regular continued fraction, you have infinitely many places to make a choice, and you can make choices as to more than one of those locations at the same time. You can do a certain insertion, then another insertion, then another, and it all works out. And you can do that infinitely many times. If you have infinitely many choices and all ways you can make choices produce different outcomes, then you have uncountably many different outcomes. So from our starting regular continued fraction expansion, there will be uncountably many different semi-regular continued fractions that represent the same irrational x. Moving on, we can talk about something called n continued fractions. This is where you just require all of your partial numerators bn to be the same positive integer n. If n was 1, by the way, this is just a regular continued fraction. Otherwise, you have something new where you have a0 plus n over a1 plus n over a2, etc. All of your numerators are the same n. So suppose x has a regular continued fraction expansion. From this, can we generate an n continued fraction expansion? Yes. Okay, take this largest thing here and multiply by n over n. That makes your numerator into n, but then this whole thing gets multiplied by n, so you end up with n times a1, and this numerator becomes n as well, but after that, nothing changes. So we multiplied by n over n to get this, this, and this equal to n, which means my second numerator is already n. Okay, by multiplying by n over n, we got two consecutive numerators to be n. So now I can just skip right to multiplying this fraction by n over n, which doesn't change a2 at all, because I'm only multiplying this by n over n. But it does end up doing the same thing we saw before. You get an n, an n, and an n. So if you keep doing this, every other quotient, every other denominator gets multiplied by n, but every numerator becomes n. This, however, is not the only n continued fraction expansion that represents x. If you start from the regular continued fraction, a0, a1, a2, and so forth, by taking all of the odd indices and multiplying them by n and making all of your numerators n, you'll have the same number. So if you have an irrational x, there is a way to represent it as an n continued fraction, but it's not the only way. As an example, let's show that the n continued fraction n plus n over n minus 1 plus n over n minus 1, etc. converges to 1. And the point of this example is that not every other denominator is divisible by n. Okay, none of them are. They're all n minus 1. So what's p naught over q naught? It's a naught over 1, that's n over 1. p1 over q1 computes to n squared over n minus 1. And in fact, Pn plus 1 and Qn plus 1 follow this recursive formula. Okay, once we're past that 0 index, all of the a's are n minus 1, all of the b's are n. So one can inductively prove, for the numerator it's quite easy, for the denominator it's a little tricky, that Pn is n to the n plus 1, capital N to the little n plus 1, and Qn takes this form right here. For as long as capital N is bigger than or equal to 2, that capital N to the n plus 1 is growing exponentially and everything else is not doing very much, so the ratio converges to 1. Even beyond semiregular continued fractions and n continued fractions and generalized continued fractions as defined at the beginning of this video, you could do something like this. Okay, so we've got a numerator, maybe it's 1, maybe it's something else, but it's got two denominators underneath it, which each have two denominators underneath them, and so forth. Okay, so each partial numerator can have 2 or 3 or who knows how many partial denominators under it, and you just sort of keep going. Notation becomes real tricky here. Convergence is also kind of weird, because before we had a limit as n goes to infinity, and n was how long you wanted to compute this. But offhand, there's no reason to impose that each of these branches has to be computed to the same depth. Okay, maybe we make that restriction, or maybe you take limits in different orders and limits in one direction and another, and you interchange limits, and swapping limits is always a huge issue in analysis. So convergence is kind of tricky to even talk about here. And so we're really not going to go into any details about these branching continued fractions. We're just going to mention that this technique of branching continued fractions like this can provide some pretty elegant expressions for algebraic numbers. So let's suppose we have an integer coefficient polynomial and we set it equal to 0. We're going to assume that the leading coefficient isn't 0 because otherwise we wouldn't have written it, and we're going to assume the constant term isn't 0 because otherwise we'd factor an x out and cancel it. Well, I can solve this by moving an a0 to the other side and dividing by x to get this expression right here, in which case I can reciprocate and we get x is equal to minus a0 over this lower degree polynomial. But now I have an expression for x. Assuming there's no issue with convergence, as I said, we're not getting into it, I can replace this expression of x with this whole thing, because x is equal to it. All of my x's in this lower degree polynomial I replace with what I know x is equal to. All of these numerators become integers, and the denominators can now be expanded. Okay, so for example, this is an times negative a0 to the n minus 1. All of these numerators are integers. That's kind of good. That's a pattern we like to see. And all of these denominators can now have x substituted in for them, and so forth, and so forth, and so forth. For n equals 2, this isn't that bad. Okay, so for n equals 2, the only term is this one. This is now to the first power, and then this constant of a1. So we've got minus a0 over a1. An is just a2. And now I just get negative a0 over a2 x to the first plus a1. There we have it. And now I would substitute this in for x again and again and again. Successive substitutions give a generalized continued fraction expansion for a quadratic irrational. If n is 2, we're talking about quadratic irrational numbers. So we end up with a not very unpleasant continued fraction expansion, and I do recommend you sort of check out what happens there. It's actually quite nice. For n equals 3, the computation is still kind of doable. So as an example, assuming convergence is not an issue, develop a branching continued fraction representation for the cube root of 2 minus 1. Now with a calculator, this is about 2599. This happens to be a root of the polynomial x cubed plus 3x squared plus 3x minus 1 is equal to 0. Compute the first three convergents in giant air quotes by just ignoring terms with unknown remainders. So from the previous slide, the formula we get is this. X is 1 over x squared plus 3x plus 1. What was really convenient in this example, incidentally, is that this minus 1, when you move it to the other side, becomes a plus 1. That's our numerator of plus 1. So the first convergent, by ignoring all of the x's on the right, is just a third. 0.33 is not that far off from 0.2599. But now if I substitute in x again, we get x squared. There's my 1 over that thing squared. Here's 3x, and here's the constant 3. If we ignore all of the x's, we end up with 1 over 3 plus 3 over 3 plus 1 over 9. And that works out to be about 0.24, which is getting closer to the cube root of 2 minus 1. Next, what we do, by replacing all of the x's we had in our previous approximation with this rational function that x is equal to, we'll end up with this. Okay, ignoring all of the x's, you get 1 over 3 plus 3 over 3 plus 3 over 3 plus 1 over 9 plus 1 over 9 plus 18 over 3. And when you compute this down, it's really getting to be quite close to the cube root of 2 minus 1. So the actual value of cube root of 2 minus 1 was about 0.2599205, and we've gotten pretty close by doing this a couple of times. So also studied in the world of general types of continued fractions, you could use non-real values. You could use what are called Gaussian integers, so complex numbers with integer coefficients, so an integer plus or minus an integer times I, as your numerators and denominators. You can do multi-dimensional constructions where the partial quotients aren't just numbers, positive integers, or even Gaussian integers, but maybe a vector. And there are even more exotic things that you can do. Generally, if you have an object and you do something similar in spirit to the Euclidean algorithm to produce a sequence of integer-like objects, and then you have a recursively defined sequence using these integer-like things that you spit out, which sometimes converge back to the original object that generated them, that's called the generalized continued fraction. Start with a thing, spit out objects to recursively define approximations that hopefully converge back to the object. This is your generalized continued fraction in general. Which leads finally to a discussion of Hermite's problem. So we're just going to mention this. It's essentially a consequence of the Euclidean algorithm that rational numbers are exactly the real numbers whose regular continued fraction stops. And rational numbers are algebraic numbers of degree 1. So there is a pretty elegant way to use regular continued fractions to discuss, is a number an algebraic number of degree 1 or not? And then Lagrange in 1770 gave this proof that quadratic irrationals are exactly the ones whose continued fraction expansion is eventually periodic. So for an algebraic number of degree 2, we have a nice continued fraction characterization. So Hermite asked in 1848, if you have an x, could there be some sort of process like this, where the sequence of objects created is eventually periodic if and only if x was algebraic of degree 3? In general, if you have algebraic numbers of any given degree, is there some sort of generalized continued fraction procedure that when acting on x produces an infinite but eventually periodic sequence of objects exactly when you start with an algebraic number of degree n? There has been some progress on this problem. This is really not something I'm terribly well versed in, but Nadir Muru and Oleg Karpenkov have shown within the last decade a lot of really nice progress in the degree 3 case. But in general, for algebraic numbers of higher degree, this is still very much open and we're not really sure what's going on.